the universe should be slowing down. Instead, in 1998, two teams studying Type Ia supernovae found evidence that it was accelerating, and the cause is still unknown. Saul Perlmutter's Supernova Cosmology Project and the High-Z Supernova Search Team were not looking for a slogan. They were measuring cosmic history. Gravity should have been slowing the cosmic expansion, the way a thrown stone eventually loses speed, but the explosions came back dimmer than expected, farther than expected. If we misunderstand this, we misunderstand the future of everything. Something was making the universe run away from itself, and we still do not know what. That is the first crack in the story. Not a monster, not a glowing object, not something a telescope could photograph and circle in red. The clue was distance, brightness, and a question that should feel almost personal. What if the quietest thing in the room is the thing deciding the fate of everything? Before that discovery, the emotional picture was simple enough to hold in the hand. The Big Bang began the outward motion. Gravity, from galaxies and matter, pulled back. The future depended on who won that tug of war. Maybe the universe would expand forever. Maybe it would coast. Maybe gravity would someday pull everything back into a cosmic collapse. But all three pictures shared one assumption: gravity was the brake. Then the supernovae refused to behave. A Type Ia supernova is useful because it can be treated as a standardizable candle, not magically identical, but regular enough after correction to serve as a cosmic distance marker. If you know how bright the explosion should be, measure how dim it looks from Earth, and compare that with redshift. You can connect distance with look-back time, how far away it is, and how long its light has traveled. The surprise was not one lonely star, it was a pattern. The distant explosions looked too dim for the old slowing universe expectation. That is the first reveal. Dark energy begins as a measurement problem, not a fantasy answer. Scientists did not wake up and invent a mysterious force, because it sounded dramatic. They were trying to explain why the universe looked farther along in its expansion than gravity alone seemed to allow. But here is where the human mind starts to fight the evidence. We are built for local things. A stone, a door, a storm, a face turning away from us. We understand a push when a hand pushes. We understand a pull when a rope tightens. Dark energy is different from dark matter. Dark matter acts like unseen gravity holding structures together. Dark energy is harder because it is not a hand in space pulling galaxies into place. It is not a wind blowing through galaxies. It is the name for the unknown cause of accelerated expansion, not proof of energy in the ordinary substance-like sense. That name can help, but it can also sedate curiosity. Once we say dark energy, the brain wants to file the mystery away as if naming a wound heals it. It does not. The label is honest only if we remember what it means. Something appears to be making cosmic expansion accelerate, and we still do not know exactly what that something is. Could the answer be empty space itself? That is the unsettling possibility behind the cosmological constant. Einstein once introduced a term into his equations that could act like a property of space. Later, after evidence for an expanding universe became clear, he reportedly regretted it. But the idea did not die. It returned in a stranger form. Maybe empty space has energy of its own. If that sounds harmless, pause on it. Empty space is the place we usually treat as nothing. The gap between objects. The silence between words. The blank part of the page. But in modern physics, emptiness is not necessarily dead. Vacuum energy is one candidate for why expansion accelerates, but it is not proven to be the same thing as the observed dark energy effect. In the simplest cosmological constant picture, if space itself carries a tiny energy density that does not dilute like matter, then as the universe grows that effect can dominate the cosmic future. Space is not just the stage, it may be one of the actors. That is a beautiful idea, but it brings a painful problem. Simple quantum expectations for vacuum energy do not naturally match the tiny value astronomers infer. The mismatch is not a normal rounding error. It is one of the deepest tensions in physics. In simplified terms, theory and observation are separated by a gulf, so absurdly large that it feels less like a math mistake, and more like finding a house key that is the size of a continent. The door is real, the key is wrong. The next reveal is sharper. Dark energy may be connected to empty space, but the cleanest version of that idea does not yet land cleanly inside our theories. The mystery is not only that expansion accelerates, the mystery is why the acceleration is so small, so persistent, and so difficult to derive from what we think we know. And the story does not rest only on supernovae. Scientists also look at the cosmic microwave background, the afterglow of the early universe. They study baryon acoustic oscillations, fossil-like patterns in how galaxies are distributed. They measure how clusters of galaxies grow. Each test asks the same question from a different angle. Does the universe behave as if a dark energy-like component is shaping its expansion history? And again, the answer keeps leaning yes. This matters because one measurement can fool you. A pattern across different measurements is harder to dismiss. Supernovae tell a distant story. The cosmic microwave background gives a young universe snapshot. Galaxy clustering shows how matter gathered over time. If all of them point toward a universe dominated today by something unlike ordinary matter, the mystery becomes less like a rumor and more like a map with the same blank region drawn again and again. But there is another possible turn. What if dark energy is not a substance or vacuum energy at all? What if gravity itself behaves differently across enormous distances? General relativity works extraordinarily well, but dark energy pushes us to ask whether the theory needs modification on the largest scales. That possibility is dangerous in the right way. It does not throw away evidence. It asks whether the rules we trust locally remain complete when the whole universe becomes the experiment. Notice the psychological trap here. When a mystery is too large, we often choose the answer that protects our favorite instinct. Some people want empty space to have energy because that keeps gravity intact. Some want a new field because it gives the unknown a moving character. Some want modified gravity because it avoids adding another invisible ingredient. Each option says something not only about the cosmos, but about the kind of explanation the human mind finds comfortable. A good episode should not pretend all choices are equal. The cosmological constant remains a leading simple model, because it fits a large amount of data surprisingly well, but simple is not the same as explain. A lock can be simple and still unopened. The honest statement is, the acceleration is well supported. The underlying cause is still unresolved. The phenomenon is not weak. Our explanation is. The standard lambda CDM model fits much of the evidence well, but future surveys ask the harder question, is dark energy constant, changing over time, or pointing to gravity itself? Then the mystery turns emotional, not just scientific. If accelerated expansion continues, distant galaxies may eventually move beyond our observable reach. Future observers in a far older universe could look up and see a poorer sky, not because the galaxies stopped existing, but because space carried them beyond contact. The universe would not become smaller, it would become lonelier. That future changes the feeling of the present. We live in a rare era when the cosmic evidence is still visible enough to reconstruct the larger story. The afterglow is still measurable. Galaxies still mark the pattern. Supernovae still carry distance clues across time. If the sky is an archive, dark energy may slowly close parts of that archive to future eyes. This is where philosophy enters quietly. We often assume absence means weakness. A person who says nothing has no power. A room with no sound has no pressure. A blank space on a map means nothing is happening there. But life teaches the opposite. Silence can steer a family. Absence can shape a childhood. The thing not said can decide the future of a room. Dark energy is not proof of that metaphor, but it rhymes with it. What looks empty may still have consequences. The question then becomes less childish and more useful. Not, what is the spooky force? But, what kind of universe lets emptiness participate? What kind of theory can respect the measurements without pretending the label is the explanation? What kind of mind can admit that reality may be moved by things it cannot picture? The final answer is not final. Scientists can measure expansion, compare models, test structure growth, and build surveys like Euclid to map the dark universe with more precision. They can narrow the possibilities. They can catch contradictions. They can make the unknown smaller, especially by testing whether dark energy behaves like a cosmological constant or changes across cosmic time. But the cause behind cosmic acceleration remains one of the largest open questions in science. So the final turn is this: dark energy is not the story of nothing. It is the story of our mistake about nothing. The universe did not simply hand us an invisible force. It handed us a lesson in humility. The quiet parts of reality may not be empty at all. The story began with dim explosions that should not have looked that way, and it ends with a larger unease. The quietest thing in the room may still decide where every galaxy goes. If space itself can help shape the future, then the most dangerous word in science may be nothing.